Thanks, Paul. My talk may be slightly shorter than Paul's introduction, but thank you very much. I want to say thanks also to Joe Kim, who can't be here. He's otherwise occupied. I want to wish him the best of luck in his adventures today with Jen. I'm going to be talking about the other end of the lifespan that he's dealing with today. Today I'm going to be talking about aging and vision in particular, and how aging influences our brain and how our brain influences vision as a function of aging. I wanted to start off by making it clear that I'm not talking about work that I did in isolation. All of the work that goes on in the lab is really a group effort. Donna Waxman is here. She's our research assistant, just celebrating 15 years at McMaster. And I'm embarrassing her by saying that, but she needs to be embarrassed. Sorry, let me go back here for a second. I'll just go on. So thank you to all of the people, the students and the collaborators who have helped us with the work through the years. What you're seeing here is a series of images that show me rapidly aging as I'm standing in front of you. You can see the two images from the starting point and from the final point here. On the left is an image that is an illustration of what I looked like a few years ago when I was 40. And if I should be so lucky, this is a simulation of what they expect that I will look like should I make it to 90. So it's not that bad for 90. Now, the chances that I might make it are actually increasing. So because the lifespan is increasing across the developed nations. And in fact, a recent study that was put out suggested that kids who are born in nations that have long-lived citizens, if you're born in the year 2000 or over, you've got sort of a 50-50 chance of making it to 100 these days. So hopefully Joe and Jen's kid will live a long life. In this case, I was born before 2000, so I'm hoping I can make it to 90, and if I do, that would be great. But I'm not the only one who's aging. This is an example of what's called a population pyramid, and this is meant to show you how Canada is aging as a whole. And this is true not just for Canada, but for all of the sort of the developed nations. What's shown in this kind of an illustration is the numbers of people in different sorts of age groups. And it's called a population pyramid because traditionally it was shaped like a pyramid. So as you go vertically up, it tells you how old somebody is. So youngest kids on the very bottom, going to older and older and older people as you go higher. And the width of those bars tells you how many people there are, right? So the pyramid shape simply means that traditionally there are a lot of little tiny kids and fewer older people. What's shown here is the population pyramid in dynamic form for Canada from about the year 1990 predicted through to the year 2050. So what you can see is here, already it's not pyramid shape because we have that baby boomer bulge kind of going through. And as we approach 2050, it becomes a population T. So in this graph, the fastest growing group is the 80-plus crowd. And that is going to have tremendous impacts on all aspects of our lives. What we see here is sort of the population estimates for Canada in particular. This is the numbers of people who are 65 or older within Canada. This year, there were estimated to be about 5 million people who were 65 or older in Canada. And within the next 25 years or so, that number is going to more than double. We'll have about 25% of the population are expected to be 65 or older. That's not just something that's happening here in Canada. As you know, this baby boom generation isn't just a Canadian phenomenon. We had the first group of baby boomers turn 65 this past January. And last year, there were around the world an estimated about 500 million people who were 65 or older. By 2050, we're expecting that number to grow to about 1.5 billion. Okay, so that is a huge change in our demographics. It means that by 2050, we're actually expecting to have, more, for the very first time in history, more people who are 65 or older than there are 5 or younger. So it's flipping that population pyramid right on its head. And basically what that means is we're going to go from seeing more signs that look like this to signs that look like that. And it's obviously going to have a huge impact on every aspect of our lives, from workforce to healthcare to recreation and transportation. And the message I want to give you today is that vision is critical in every single one of these aspects of our lives. Vision affects everyone. And when I'm talking about vision, I'm going to focus on the work that we've done primarily in our lab and in labs around the world that focus on healthy aging. But it is important to know that there are a number of deficits that are typically associated with aging as well that affect vision. And these are just a couple of the examples of the kinds of things that through the aging process you might expect to have happen as you get older. There are 4 sort of main categories, including age-related macular degeneration. It's estimated right now about 1 million people in Canada suffer from one form or another of what's called AMD. What's shown in these images is if you had a street scene, sort of what the world would look like, a simulation of what the world would look like to one of these sorts of patients. And you can see AMD is particularly debilitating because you kind of get the opposite of this tunnel vision here. You get a negative tunnel vision. You can't see what's right in the middle where you're looking. And I can bring you into the lab and do experiments with you with our eye tracker and simulate this for you, and it is the most frustrating experience in the entire world. You try to look at something and it disappears. So you look at something else and it disappears. And people with AMD develop all kinds of strategies to adapt, but it's important to know that this is actually a huge impact on the Canadian society. Glaucoma, about 250,000 people in Canada suffer from this. That tends to give you deficits more in your peripheral vision, sort of what's off on the side. Cataracts, about 2.5 million people. So it's a much bigger impact in terms of the numbers, but it's not as devastating because we now can treat this pretty easily by replacing the lens. So it'll look blurry to someone, for example. You can put an artificial lens in and then you're okay, by and large. And this is something that's increasingly important to think about, the diabetic retinopathy, because diabetes is really on the rise. And these are problems with the retina that are associated with diabetes. And so as we start to see an increase in the numbers of diabetes cases around Canada, we're going to have to start thinking much more carefully about what the visual impact is of diabetes as well as the rest of the health impacts. Just to bring these numbers home a little bit for you, this number here, AMD, 1 million people in Canada, it's estimated that there are about 500,000 people who have Alzheimer's disease in Canada right now. So everyone talks about Alzheimer's, and Alzheimer's is a really critical disease. As of last year, for example, a new case of Alzheimer's was diagnosed about once every 5 minutes. And if we don't change the way that we're able to think about the brain and work toward curing Alzheimer's, we're going to start to see a massive, what we call the Alzheimer's tsunami, so that within a generation we'll start to see one new case diagnosed every 2 minutes, which is a huge increase. But having said that, age-related macular degeneration is affecting more people than currently affect Alzheimer's, Parkinson's, breast cancer, and prostate cancer combined. So that's a very big issue, and it's the leading cause of blindness in our older population in Canada today. So it's something we need to be thinking about more in the future. I'm going to be focusing not so much on what happens when the visual system goes awry, as in these cases of visual disease, but what happens even in the case where you're free of these sorts of diseases. What happens in sort of the standard aging sequence? And this is one of my very favorite quotes. It's a quote from a chapter that was written back in the 80s. And when the chapter was written, this was a chapter on aging and vision, back sort of at the beginning of when people were really studying aging and vision. They actually had a person on this panel in Washington who was an aging vision researcher. I don't mean someone who studies aging vision, I mean someone who was rapidly aging. He was aged. And they asked him to think about his own sense of what was happening to him as he was aging. So this is an introspection from this researcher. And what he said is the following: just plain seeing in simplified situations, as in routine vision testing, seems as good and as quick as ever, but perceiving the meaning of a complex, changing scene is definitely more difficult and slower. And I think when we saw that quote, it really brought home for us some of the things that we were hearing when we were talking to our grandparents or our parents or the participants in our experiments, and that is that they'll go to the eye doctor and they'll go and they say, I can't see, something's wrong, and the eye doctor will say, you're fine. And they come out and they feel very frustrated because they don't feel as though their issues have been addressed. And when we started thinking about why that was, why is the eye doctor on the one hand saying nothing's wrong with you when the person themselves, they know something is wrong, they know that they're not seeing as well? We started thinking about what kind of tests are being done in the clinic versus what the real world tasks are. And so what's shown here is an example of a sort of a typical kind of task you might see in the eye doctor, or we might run in the lab as a screening device. This is just a Snellen and eye chart. You have to just say what the letters are, and you might start here, F, B, C, P, T, E, O. See how far down you can go, and then we can see what your vision's like. In the real world, you might be having to do something like this, driving in a very complex scene with bicycles coming out and pedestrians hiding behind trees, and things moving all around you, a cluttered environment, you don't know what to expect. And there are real differences when you think about what happens in the clinic and what happens in the real world that we think might explain why the eye doctors say you're okay when you don't necessarily think that you are. And specifically, when you're at the eye doctor, there's no time limit normally. So, I can be looking at this third line and think, B? Z? Right? And that's okay. I'll still get it right. I'm not being timed out. In the real world, if I do that while I'm driving and someone steps in front of my car, that is going to cause a problem. So in the real world, there are real time constraints. In the clinic, there are not. You have relatively clean scenes. So even there's a little bit of clutter, it's black on white, and you know exactly what to expect. These are all letters that you're familiar with. And in the real world, you don't know what to expect in your visual scene from moment to moment. It could be anything different. You could have someone jumping out from behind a tree one time and not another time, and you can have rooms filled with clutter and so on. And you can have to be driving through a snowstorm, particularly if you live in Canada. We've been lucky so far in October, but I'm not counting on it lasting. And so those sort of things, you're not simulating those kinds of visual environments, that noise and that clutter and that unexpected environment in the clinic. And the final thing, which I think is really important, is that typically when you are doing one of these tests within the clinic, you're only doing one test at a time. It's a single task. What's the letter that you see? Tell me if you see a spot appear somewhere out in your peripheral visual field. Okay, how often in the real world, these days especially, are you really just doing one thing at a time? Almost never. We're almost always multitasking. We're almost always trying to do multiple things at the same time. And so if you're testing people under these conditions, it's no wonder that it doesn't necessarily map onto what's happening in the real world. So the approach that we were taking in our lab was to try to figure out if we push the limits a little bit more and try to sort of simulate within the laboratory conditions what happens in the real world, will we start to see some deficits as a function of healthy aging? So that's the kind of approach that we took. And some of the sorts of things that we've done are to use a combination of different sorts of techniques. So in some cases, we use behavioral methods. In other cases, as I mentioned, we might have used eye tracking. We use fMRI, functional magnetic resonance imaging, brain imaging. And we also use something called electroencephalography, or EEG. And this is an example of one of our participants who actually just passed away at the age of 102? Roughly 102. He was in his 103rd year. This was taken, I think, on his 98th birthday when he came into our lab to run an experiment. I have another picture, which I'm not showing, which has him with a birthday hat on top of the EEG cap, which is really cute. And this fellow is an amazing participant. What the cap tells us, though, is what's happening in terms of the timing of his brain when he's doing different kinds of tasks. So he was actually a participant in one of the experiments. We were looking at an aspect of face perception. So how well can older people process faces, which is really important if you want to maintain social interactions throughout your life. And more importantly, how is both the behavior related to sort of the timing of what's happening in the brain. And what we did here was basically just to say you have to discriminate, for example, between these two faces. So these are two different women. And here, all of the information about the structure of the faces is present. If you go over to the left side, what we've done is to randomize all the structural information. It just looks like these little clouds of noise. So it's a lot harder to tell which stimulus is which in that case than it is over on the right-hand side. And then, of course, we had everything kind of in between. So we go from no structural information to 100% and then in between. Behaviorally, what we were looking at is the extent to which older people could make use of that structural information. And when we looked at the behavior, it turned out that the older people were basically just as good as the younger people, a little bit worse, but the pattern was pretty much the same for younger and older people. When, however, we looked at the pattern of activation based on this EEG recording, we saw something that was a little bit different. And what this shows is for each individual subject in each of these rows, an estimate of when the peak information for the face discrimination task is being correlated with the activation in the brain. And basically what you can see as a function of time from the beginning of the stimulus coming on to 500 milliseconds after, half a second after, where it's red, that's when you have the highest correlation. So basically what this is showing you is that for young subjects at about 150, 170 milliseconds, you see a really strong representation of that face information in the younger brains. In the older people, first of all, you see there's more variability in the strategy. So this older person, who might have been the fellow, the 98-year-old, he always acted like a 20-year-old. Some people actually look sort of like the younger people, but a whole lot of our subjects look quite different. So there's more variability in the older people, and B, you've got a delay, basically, in the time that it's taking our older people to process this information. So they're getting the information, they're able to use it, but it's just taking longer to get through the system. Okay? This isn't something that you'd be able to pick up in the clinic, but it is something that could have really serious impacts on daily life, especially, for example, when you're driving. Now, we can see the impact of timing not just in face perception, but in other sorts of tasks as well. And this is one task that we published recently for work that was done with Eugenie Rodea and Lindsay Farber, along with Pat Bennett, my colleague. What the task here is basically to say whether if you look over here, you might see there's this sort of the C contour that's embedded in those background elements. Can people see that? It might depend on where you're sitting. There's a gap in the C. In this case, it's located sort of down here. In this case, there's a gap in the C, and it's located over here. This one might be a little bit harder to see because of the structure of the stimulus, but the gap is actually over here. So people had to look at these sorts of stimuli, and we asked, how long will it take you to be able to tell where that gap is? Okay, so we showed them one of those stimuli, and we varied the duration. We masked it with a noise mask, and then we said, where was that gap in the C? And we just wanted to know how long would older people take to do this, how much time did they need to extract the information versus younger people. And what we found is the following. So for the three different sorts of conditions, the easiest, sort of the intermediate, and the hardest, you can see for younger in white and for older in these gray bars, the pattern is pretty much the same. There are some interesting differences, which I can go into later if people are interested, but the pattern is pretty much the same. This is easiest, second easiest, and third easiest. But if you look at the effect of aging, the older people are taking significantly longer in each of those cases to be able to extract that relevant information. So again, as with the faces, they can get the task done, but it's taking them longer to get to where they need to be. So timing is really critical. Now, the other thing that's interesting in this particular example is I showed these sorts of C things, and they were embedded in noise. So this is bringing in this element of clutter, the noisy environment. So it's not that there's a really clean stimulus that they're looking at. It's more, again, like the real world. And you can see these sorts of effects of clutter or noise not just in static images, but also in moving images. And these are some images that we've used in a range of studies on biological motion with our former postdoc, Karen Pills, and we're doing some other work with Justine Sargent on these sorts of stimuli with aging, but also with schizophrenia. And what you can see here, well, actually, can anyone tell me what do they see over on, say, the left side? A person walking. Okay. In both of these cases, there's actually a person walking. I've embedded the person in noise over here, and there's no noise here. And the task of the subject is just to say, what direction is the person walking? Is the person walking this way, or is the person walking this way, right? So when you look over at this image, do you say the person's moving to the left or to the right? To the right. And when you look at this image, is the person moving to the left or to the right? Left. And in fact, you're correct in both cases. This task is a little bit harder in some circumstances. This particular condition, we've made it so it's pretty easy to see. When we look at the results for younger people versus older people, again, for the noise-free version and the noisy version, what we see for the younger people is when there's no noise, they're just about at 100% correct. This is a really easy task for them. When we look at the noise version, it's also really easy for them. They're about 100% correct still. Now, what happens with older people? For the noise-free version, it's really easy for them. In fact, they're slightly better, not significantly, but they're maybe even slightly a little bit better than the younger people on that task. But when we put the noise on top of it, what happens is that we now see for the older people, they tend to have a little bit more difficulty. So they're 20% worse now than our younger participants. And I should say, in most of the experiments, when I'm talking about younger versus older, younger averages around 20, 25, and the older average around 70. So it's usually 60 and up for the older. Was that what your question was? Yeah. So you can see here, the presence of noise is making it harder for the older people's brains to extract the relevant information. The younger people can really just sort of ignore that. So again, in the context of the real world, if there's noise out there, it's going to have a bigger impact on the older brains and their visual system than on the younger folks. Now, the last thing I talked about that was different between the clinic and the real world is this aspect of single task versus multitasking or dividing attention. And we've looked at that in a couple of different ways. I'm going to show you one example here, and I'll come back again to this a little bit later. In this case, what we're doing is we're using a task that's known as the useful field of view. And in this task, basically, it's sort of like that, part of it's sort of like that task where if you go to the eye doctor or the driver's test, and they ask you to say when you see a spot out in the periphery, there's that component to it. But we measure not just how well you can see that spot in isolation, but also while you're doing something else at the same time. Okay? So in this case, one of the tasks is what we call the focused central task. And you have to just say a letter flashes up in the middle, and was that an E, an F, an L, or an H? Okay? It's pretty easy. Then we ask people, if I flash one of these spots up in one of these locations, where was the spot? And they don't have to say necessarily exactly where it is, but what was the direction, for example, of that spot? Which orientation, what spoke was it on, basically? So that's two different kind of focus tasks. There's the localization task and that initial letter task. And then, of course, we can have them do both of those things at the same time. Now we're multitasking. We're asking people to do two things at the same time. And this is where things get interesting, because when we look to see what the effect of that multitasking is, as a function of age, we see very different things for the different kinds of tasks. So when we look to see what happens to the letter performance, so how well you can tell what that central target was when you're doing two things versus once, as a function of age, we did decade by decade from the 20s up to actually the 80s in this case. On the y-axis, we've got the effect of dividing attention. This is the error you make when you're dividing attention minus the error you make when you're focusing. So positive numbers mean you're doing worse when you're dividing attention, you're making more errors. And negative numbers mean you're actually doing slightly better. 0 means there's no effect of dividing your attention. And what you can see here is that it looks as though there's actually a slight benefit for dividing your attention in the letter case. We think that's because of the order in which the experiment was run. But most importantly, there's no effect of age whatsoever. Okay, so whatever the effect is of dividing attention, it's constant across age. So these were easily visible stimuli and so on. Yes, Sigal? In this case, there was no sex difference. I can come back to sex differences later if you want. We do see some in some tasks, but not in all tasks. So. Yeah, there is some evidence actually, as an aside, women are better at multitasking. So you can tell them that's a scientific fact if you want. In this case, we didn't find it, but there's other experiments. In this case, when you look at the effect of location and dividing attention, here we see a humongous age effect. It's actually quite linear. So decade by decade by decade, you get worse and worse and worse. So what that means is that this age group actually was 15 to 24. You peak at 15, and then it's downhill from there. Okay? That's not good news. And it's especially not good news because if you know anything about the driving literature, you may have heard that the kind of tests that we usually do to test driving to see if you're able to get your driver's license here in Canada and in most parts of the world actually are not correlated with driving ability. So for example, if I ask what's your visual acuity, I measure one of those Snellen charts, the eye charts with the letters. The performance on that, unless you're completely legally blind, performance on that does not really predict accident rates. Performance on this kind of task, decade by decade by decade, that actually does correlate with driving accident rates. So what this means is that there's actually a potential implication for, again, our everyday activities here. And I can come back later if people want to a discussion of why is it that the government, even though it's been shown over and over again that this sort of measure is correlated with performance on driving tasks, why do they still persist in using the other task? That's a different discussion, maybe a political discussion. But it's clear that if this actually is related to driving, we should expect that it might have an impact on the ability of our older people to be driving safely under a number of conditions. And I'll come back to this again in a bit. So there are, again, a whole range of tasks in which we do see deficits in healthy older adults without macular degeneration, without glaucoma, cataracts, etc., just as a normal function of aging. We don't necessarily see those in the clinic, but we can see them in the lab if we put people into the right sort of conditions. And effectively, what that is saying is that in the real world, we might be having our older people going from seeing a scene like this to seeing a scene that looks more like that. And you can imagine how much more difficult that would make it for older people to be functioning in the real world. Now, I'm not going to end there because that's depressing to end that way. So I'm going to go into a more positive side of the story, which is the fact that when people first started thinking about vision and aging, it was in a very different context about the way we thought that the brain worked. Okay? So it used to be sort of believed that there's a lot of change in babyland, as you're developing as a child through, the first few months and even maybe in some cases a couple of years of life. But then once you're an adult, your brain was pretty much fixed or maybe just started to fall apart, right? It was then discovered, but only as recently as the late 90s, that throughout our lifetimes, we actually can have new cells born in our brain, and this is called neurogenesis. And it's really amazing to me that it was really only just over 10 years ago that this was discovered. Okay, so it was just 1998 is when it was reported new brains can be growing in the cells of adult animals, in this case, throughout our lifetimes. We still don't really know what those new cells are doing, but it gives hope. It gives a suggestion that the brain is not fixed at adulthood. It's constantly changing. And that suggests that maybe not everything's going to fall apart. All right? And in fact, when we've looked at different kinds of tasks in our lab, we do see some things get worse, but we see some things stay the same or even get better. And this is an example that I'll show you of one of the things we found that actually gets better. And this, I think, is what got us into Oprah's magazine. So Oprah's into this kind of stuff, I guess. Paul, you were in O magazine too, right? David Feinberg was. Yes. So it's like a common thing in our department, I guess. But he was in the before and after makeover section, I think, right? So that is different. Okay, so in this case, I'm just showing you part of what this experiment is. And really, it's a very basic experiment. It's very easy. All the people have to do is say, you've got a high contrast moving set of bars. In this case, they're small. In this case, they're big. Are they moving to the left or to the right? So if you look at this one, does it look as though it's moving to the left or to the right? Right. And if you look at this one, is it moving to the left or to the right? Right. It's pretty easy, right? So what we did was basically to look to see, again, how long it took people to make this kind of a judgment. So we could present these things for very short periods of time or for much longer periods of time, and we estimated what's called a duration threshold. So how much time do you need to be able to get, say, 80% correct on this task? And that's what's going to be plotted here. So short times means you're really good. You can see this quite quickly. And longer times means you're worse and you're taking more time. And in this case, with the younger people, what you can see is that when the target is very small, it takes about just under 60 milliseconds to be able to do this task. Okay? So they need to see the thing for 60 milliseconds to be able to make reliable judgments. Interestingly, what happens when the target is big is they get even worse. And that might sound counterintuitive, because usually you think if you make something bigger, it should be easier to see. But there are people who originally studied this phenomenon, G.A. Tadden and Joe Lappin and Randolph Blake and others. What they suggested was this is actually just a byproduct of the way that the visual system is organized. We have these things called receptive fields in our visual system. And basically, if something is low contrast, like this grading here, it's hard to see, like sort of light gray, dark gray kind of thing. If you make it bigger, it's going to be easier to see. You're summing the information, right? But it turns out that if something's high contrast, our brains are actually set out to inhibit things as they get bigger. And the reason for that is because the idea is that when you're looking at high contrast things, you're supposed to be looking for objects, right? And if I want to see an object, if I see a whole wall full of something, that's not an object, that's a background. So our brains are kind of tuning out the background and trying to tune into the object. So for high contrast, we have these inhibition systems kicking in young people. Now, for various reasons, we thought there might be differences in inhibition in older people, so we ran the same experiment there. And what we saw there was for the smaller objects, older people took longer. So again, this is their slower. That's, everyone says older people are so slow. Well, here they are, in fact, slower. But when we looked at the bigger object, we actually saw in this case, older people are faster. Okay, so it's not the case that older people are always slower. In this case, and this is why it ended up in O Magazine, this was a case where older people are better and faster. Hooray! And so that was a very unusual sort of finding. It makes sense, though, if you think about the idea that what might be happening in the brain as we get older is there are changes in our inhibition system. In particular, we think there might be a link to what's called the GABAergic system, GABA. These are data that were collected by Kathy Murphy's group here at McMaster, looking not at how much GABA is in the brain, but a precursor to GABA, which is called gefferin, which is an anchoring protein for GABA. So if you look at how much gefferin there is in brain slices from humans at different ages who unfortunately passed away at different ages, and then you can see what happened to their brains afterward, what you can see is the amount of gefferin expression increases sort of through the teenage years and then starts to decrease. So for this 55 plus group, which was their oldest group, you can see there's much less expression of the gefferin than there is sort of for younger adults. And that is an indirect suggestion that there's less GABA in the system of older people, which is potentially correlated with having less inhibition. And I can later talk about some of the physiological evidence for this as well if people are interested. But the idea here is that if there's less inhibition in the brain, in the sorts of parts of the brain that we're thinking are influencing performance on this task, we're not going to be suppressing that background as much. So we're actually going to be able to see the big things better. All right, so the idea is maybe that younger people might be able to get sort of, when they look at something like this, it might be hard for them to sort of see what's going on at the individual level because they're sort of suppressing the whole thing. Older people might be able to sort of see the whole gist, but if they need to figure out where that ball is, in this case, they might have a harder time sort of tuning in on that, right? So the idea is potentially, at least in some situations, older people can maybe get the gist of something, the big picture of something, but will have problems sort of tuning in on the finer details, okay? So there's kind of this trade-off. But it's not the case in this case that older people are always worse. In one case, they're actually better. In another experiment we did, we wanted to know what's happening in the brain as a function of aging, and whether things that are getting better or worse are staying the same, how that's being sort of implemented within the context of the brain. So in this task, again, it's a very simple task. I'm going to show you this stimulus, which is a set of bars, and then another set of bars. And I want you just to say which interval, the first interval or the second interval, had thinner bars. So interval 1 or 2. So here's interval 1, and here's interval 2. Which has the thinner bars? 2. You guys are excellent subjects. Donna, sign them all up. Now I'm going to do it again. So here's interval 1, and here's interval 2. Which one? Who says 1? Who says 2? Okay, it's 1. You guys failed that task miserably. This is about a 10% difference. The first was about a 100% difference. I doubled it. This is about a 10% difference. And that's actually the measurement that we were getting in this task. We wanted to know how much of a difference in that bar width do people need to be able to make this judgment reliably. And we could show these things for very short amounts of time in between the two intervals or for longer amounts of time in between the two intervals. And we were looking to see how does performance change as a function of age here. This is really a very basic visual memory task, really. And so we had interval 1 and what's called an interstimulus interval, which is a blank period, either half a second or 4 seconds, which in vision is a long time. And then interval 2. And they just had to respond which had the thinner stripes, 1 or 2. When we did that, we were simultaneously measuring the activation within their brains. Now, we actually used positron emission tomography for that study. This is an image from functional magnetic resonance imaging, but I'm just trying to convey the idea here, for people who don't know this, that you can actually see what's going on in the brain, basically, and how it relates to what's being shown on the screen using these kinds of brain imaging methods. So in this case, we're alternating. These are actually real data. We didn't actually cut the person's head open. That's done on computer software. But we do show, for example, let me go back there. You do show, say, either a disc in the center or the donut around it. And what you can see back here is that different parts of the brain are representing those different sorts of stimuli. So you can use these kinds of techniques and then try to figure out how does the activation in the brain correlate with or predict the performance for the different sorts of groups. So first, how do they perform? At the short interval, stimulus interval, and the long, 0.06 here means you needed a 6% difference in the bar width to be able to perform accurately. 0.14 means you need a 14% difference, and you can probably guess where the data are going to end up given those numbers. For young people, you needed about a 6% difference at the short interval and about a 14% difference at the long interval. I showed you 10%, and you had problems with that, so these are pretty good. These are pretty good subjects. Of course, it was more controlled settings. Now, what happens with older people? When we looked at the older people, it was impossible to know who was old and who was young. If you just looked at the data, they were identical. The spreads were identical, the means were identical, everything looked the same. So the older people were looking exactly like our younger people on this task. But we wanted to know, why is that? Is it just that they're still young in their brains, or is there something else going on? And what we found in this case was that when we looked at the system of brain areas that was actually linked to performance, we saw something really interesting. In the young people, the system involved a number of regions, but most importantly, that shown in blue here and then these in the red here. The primary system was obviously this one back in the back of the head. This is the occipital cortex, and if you know anything about the brain, you know this is sort of where the primary visual processing happens. It's a visual discrimination task that makes a lot of sense. Young people are making use of that part of the brain. Now, when we looked at what happened in older people, though, this system wasn't really working that well, but instead, this system here, shown again by the blue and the red in darker, more saturated colors, that was driving performance. And what's interesting there, if you know your brain anatomy, which I'm sure all of you know extraordinarily well, this is bringing in parts of hippocampus and prefrontal cortex. And hippocampus in young people is usually associated with memory. Prefrontal cortex is usually associated with attention. And our older people seem to be using those parts of the brain to do a really basic visual task. So what we think is going on here, based on this study and a number of other studies that have come out since then, is that the older brains are effectively rewiring themselves. Okay? There is a weakness in the system that they used when they were younger, but they're compensating by bringing in these other systems. It's sort of like if you have two piggy banks and you're saving up, you've got your everyday savings and you're saving up for a wonderful trip to Hawaii. Okay? Now, if I've got lots of money already in my Hawaii piggy bank, but I don't have any money in my everyday account, I could borrow. I could borrow from my Hawaii account to buy shoes or food or whatever it is I need for every day, which is fine until I want to go to Hawaii, and then I'm in trouble. And you can think of this the same way. If I'm borrowing to do a very basic visual task from my memory system or my attention system, that's fine until I need to use my memory system or my attention system, and then I'm in a lot of trouble. Okay? So what we think is that one of the reasons we start to see effects of aging when we make the task more complex, when there's noise involved, when you're doing dual tasks and so on, is because the visual system, the brain is basically giving priority to the sensory information. It's saying, you know what, if I can't see it, if I can't hear it, it's not worth paying attention to or remembering because it's not in there in the first place. So you kind of have to give priority to the sensory information, even if that means borrowing from your memory system or your attention system. Okay? And that's going to work for very basic things. But once you start to stress the system a little bit, you can't go to Hawaii. Right? You're going to run into problems. You won't be able to remember things as well, and you won't be able to attend as well. And in fact, when you think about the literature, which everyone's just read about in the newspaper, where do we normally see big effects of aging? It's in areas like memory and attention. We think that actually may be sort of a byproduct of the brain reorganizing itself to protect the sensory input, which if you don't have that, there's nothing to remember or to attend to. Now, one of the things that we found really interesting was, again, back this idea that there can be this reorganization. We know that there are new brain cells that are being built throughout our lifetimes. So what that would suggest is that maybe we could train older people to compensate somehow for what seems to be happening in a really natural way. And so to look at that, we went back to this divided attention task. But we had people come back a number of times. So we had them come back for initial test, and then we tested them over 9 days, and they had to come back 1, 2, or even 3 months later to see what happened. And just to refresh your memory, what we have here is, this is just for the peripheral task here, this localization task of that dot that I showed you before. These are the results from that last experiment that I showed you, just for the sort of the 20-year-olds versus the 70-year-olds, for example. And you can see that both people have an effective divided attention, but older people are being more affected by dividing attention than younger people. Well, the first thing we wanted to do was to see if we give them more time, the older people, can we help them catch up that way? Because as I said before, older people sometimes need more time to be able to process information. So we did that. We gave younger people only 50 milliseconds to see something and older people 90, and all of a sudden we can equate performance. They're both still having some problems, but the older people have gotten much better. Now we bring them in for 9 different sessions. We want to see what happens as a function of that learning. And what you can see is shown here, the younger in yellow and the older in the blue. And if you look to see at what point do you consistently get points that are near that 0, remember? If you think back to what I said before, 0 means there's no effective dividing attention. You can see that both the younger, right, and the older end up at around 0 after some training. The older seem to take slightly longer to get there in terms of numbers of sessions, but both groups can get to that 0 point, which means both groups can learn to divide their attention. Okay? And now the question is, if you're training someone to do this, is this going to have an impact on things like driving? There's also a question of what's going to happen as a function of how long will it last. And in this case, we tested people after 1, 2, or 3 months without any additional practice. And you can see certainly at 2 months, this is being maintained without any additional practice after just 9 initial sessions. It's still, some sort of semblance of improvement even after 3 months, although it seems to be kind of waning at that point. So this suggests that you can, in fact, potentially turn a scene that looks like this back into a scene that looks like that. Okay? And in this case, we can teach old brains new tricks. Now, what's the next step? Well, we know that we can teach old brains new tricks. What we don't know is whether we're reorganizing that neural system yet again, or is that old system, the system that has been rewired once, just becoming more efficient and more effective. So that's one of the next things we need to really understand. How is the brain wired up? How do the different components of what we do in everyday life, how are they organized within the brain? How does that change as a function of aging? How does that interact with things like context and learning? Right? We don't know that yet, and that's, I think, one of the big questions that still needs to be answered. Another thing that we need to start understanding a bit better, and there are folks in our department who are doing some of this work, Judy and others, doing work on training and video games. So for example, can we use things like video games to train older people to improve their memory, improve their vision? Daphne Maurer's group has been working on some of this as well. And the initial suggestion is you maybe sometimes can do this pretty well. There was actually a recent report out of Israel by a group that was actually working with Daphne's group, but also working to show that really basic visual training, you can improve people's visual acuity, for example, in really long-lasting ways. This is a huge market for people in terms of selling video games to older people to improve their brains. I don't think there's enough evidence out there for the ones that are already being marketed. It's a good field for research, but I think that down the road there certainly is potential. But you have to keep in mind that the training, perceptual learning, often is very specific. So if I train you on this one thing, you'll get better at that one thing and maybe some related things, but it's not going to help you on this. So there was a study that came out recently about Scrabble playing. I don't know if people saw that, where they looked at people who were professional Scrabble players, competitive Scrabble players, and people who weren't. These were both, I think, senior groups. And what they showed was that the people who were better at Scrabble also were better at anagrams and reading vertically. Okay, so duh. That's nice, it transfers, but those are things that if you're playing Scrabble and you're really good at it, you kind of have to be able to do anagrams and read vertically because that's part of the game. But when they looked at other more general aspects of intelligence and memory and cognition, there weren't any differences there. So right now, I don't think we're at the point where we're going to find this is the one task you have to do and it's going to improve every aspect of your brain. Where we are right now is trying to figure out how can we do one task and have it improve related sorts of things? Where do we get generalization and where do we not? And the other thing that's actually increasingly interesting for us is this idea of personalized medicine or personalized training. In the EEG results that I showed you one of the kind of things we do is just to show a subject-by-subject analysis. And in our laboratory, not just in our aging research, but in some of our other research as well, we're increasingly starting to look at these individual differences. Because what we're seeing sometimes is that when you average across all of the individuals, what's seen there is not representative of any of the individuals. Right? So for example, in some work that we've done with Mel Rutherford on face perception in people with autism, in autism spectrum disorder, if you average everyone's data together, it looks like everyone kind of has some difficulty using information about the eyes for face recognition. When you look more carefully at the data there, what you see is that basically half of the people with autism are perfectly good at using the eyes, and half of them can't use them at all. So there's these two different distinct groups, but it's not until you start looking at the level of the individual that you can see what's really going on. And we see that same thing in aging. Remember in that EEG diagram that I showed you, some people look like 20-year-olds and some don't. And as you get older, the variability varies tremendously. So people do not age in lockstep. And there's a really interesting phenomenon called the terminal drop, which is the idea that if you were to plot a whole bunch of different sorts of cognitive and perceptual functions as a function of your chronological age, how old are you based on when you were born, nothing lines up. But if you track people long enough and you plot not from when you were born but from when you die and go backwards, you'll see what's called this terminal drop. I'm trying to do it in your scale. So people are good, bad. Kind of everything falls apart at once, and then you're gone. And this is Patrick Rabbit talked about this a number of years ago. So it may be that not your age, chronological age that's important, but something more about your biological age, which is sort of impossible to know for us at this point in time until we can see what happens as you progress through your senior years. So increasingly, I think what we're going to need to be doing is figuring out not just what's the normal system of, what's the optimal way, say, to organize your brain, how can we train you to do it, but what might one person need versus what might someone else need? Because I might have a deficit in one aspect of my perception or my cognition, and my husband might have different sorts of deficits, especially in your family, Sigal. You've got someone who can't multitask at all and someone who's an awesome multitasker. So you might have to have different kind of training programs that are aimed at different individuals. And you might have to have, even if it's just multitasking, you might have differences in the kind of multitasking. So I think that's where we really need to be ending up, is thinking about it in terms of individualized medicine and individualized training. So just to summarize, I have a couple of take-home messages. One is older brains change. And they don't just always get worse. Okay? So older brains are processing information differently than younger brains, and there are changes in the functional roles of the different brain regions, and there are changes in the connections among those regions, and there's potentially also changes in sort of timing and the neurochemistry of the brain, including the GABAergic system and other inhibitory mechanisms. When they're changing, as I said, they're not always getting worse. It's not just that they change and they fall apart, but there are a number of trade-offs. So for example, older people in some cases perform worse in clutter and noise, but they might be better at getting the big picture, right? And similarly, you might spare some of the basic visual processing, but that might mean that you're going to have difficulty with complex tasks. So some things are getting better, some things are getting worse. There's sort of these trade-offs that are happening in the brain. And it's also important to remember that older brains can actually learn. Okay? So the older brains are remaining tremendously plastic throughout our lifetimes. New cells are being born, but also new connections are being formed, and we can learn new things. And I think that what that does is it provides us with terrific opportunities for training, for early diagnosis, and for personalized medicine to make sure that our older people are going to live the longest and happiest lives that they can. And the final take-home message is that it's really important to understand how vision impacts with aging, because if you can't understand the basic sensory aspects, it's going to be harder to understand what happens later in terms of memory and cognition and attention and motor behavior, because everything in the beginning is going to be impacted by the information that's getting into your sensory systems. And our ultimate goal, obviously, is to ensure that Canadians are going to live long, healthy, happy, and productive lives. Thank you very much.